Good day, everyone. Today we are going to address some of the open questions that remain from the previous lectures. Specifically, what can we do if we are unable to find an MVU estimator, or if the MVU estimator doesn't exist? Or, for example, what can we do if we don't really know the exact distribution of the data, but we only know some things about it. Okay, so when can't we find an MVU estimator? So remember that the only tool that we introduced in this course to obtain MVU estimators is the application of the second part of the Kramer-Rao lower bound theorem, which provides an efficient estimator when a certain condition is satisfied. Okay. However, that condition may not hold. Okay. And therefore that method fails to provide an MVU estimator. And there are other methods to find MVU estimators, however, they may similarly fail. Okay. And sometimes the MVU estimator may not even exist, right? So remember how we arrived at the notion of MVU estimator. We initially tried to find the estimator that minimizes the MSE among all possible estimators, okay? But we showed that that task or that goal was impossible, right? And that forced us to go after a more modest goal. Okay, so we decided to confine ourselves to searching for an optimal estimator within a small class of estimators, namely the family of all unbiased estimators, right? So searching for an estimator with smallest MSE or with smallest variance in this class is the same, right? Because remember that for an unbiased estimator, variance and MSE coincide. Okay. So the estimator that minimizes the variance within this class is the so-called MVU estimator, a minimum variance unbiased estimator, right? And that one may not exist precisely because the variance, our criterion, right, is dependent on the unknown parameters, right? So it may happen that for some values of the parameters, one estimator is the best, but for a different value of the parameters, another estimator is the best, right? So therefore, that's when no MVU estimator is said to exist. Okay. So the approach that we are going to pursue today is to further restrict the family of estimators against which we compare. Remember that this is a recurrent theme in statistics. Whenever we cannot find an optimal estimator within a certain set of estimators, we just reduce the set of estimators against which we compare until we are capable of finding one that is optimal within that reduced family. Okay, so in this case we will be focusing on estimators that are not only unbiased but also linear. Okay, so the reason is that linear estimators are simple and they are easy to analyze. So their computational complexity is low, and their bias and variance or covariance are easy to obtained, right? Remember from probability theory that the expectation or covariance of a linear function of a random vector can be readily computed if we know the mean and covariance of that random vector. If you don't remember this clearly, you may go back to the review video on probability theory earlier in this lecture series. The problem formulation is the same as before. Okay, we are given data that adheres to some probability distribution parameterized by a vector theta, but in this case we are going to assume that theta can be any vector in Rm. Okay, and the goal is to estimate theta. So the estimator we are after is the one with a minimum variance within this shaded area, right? And it will be referred to as the best linear unbiased estimator. Okay, so formally an estimator is blue if it is linear. Okay, so it is in the blue circle. It is unbiased, all right? So it is also inside the yellow circle, and its variance is no greater than the variance of any other unbiased linear estimator, right? It must be the best within all linear unbiased estimators, okay? Now I have a question for you. When does the blue coincide with the MVU estimator? And the answer is very simple. It can be phrased in just 5 words, but I encourage you to stop the video and try to answer it, okay? Okay, so as you may have guessed, both estimators coincide when the MVU is linear. Okay, so the reason is relatively straightforward. So the MVU is the best estimator within this yellow circle, right? And therefore it is better than any other estimator in the yellow circle. In particular, it is better than any other estimator in this shaded area, right? So whenever the MVU estimator turns out to be in this part, right, of the yellow circle, then it is obviously also the blue, right? It's better than all other estimators in this area. So when don't they coincide? They don't coincide when the MVU estimator is somewhere in the yellow circle but outside of the blue circle, right? So in that case we may have one MVU estimator and also one blue estimator, but they are different, okay? To make our lives easier, we will be introducing a couple of assumptions. So specifically, we will be assuming that the mean of the data is a linear function of the parameters, and that the covariance of the data is a constant matrix. Okay, so by constant we mean that it doesn't depend on theta. Okay, and the same here, h cannot depend on theta. All right, so are these assumptions necessary for a blue estimator to exist? And the answer is no. If they hold, then we are warranted to find a blue estimator. However, it may occur that these assumptions are violated, but we can still find a blue estimator. However, in this lecture, we will focus on the situation where these assumptions hold. Let's start by looking at the case where we want to estimate only one parameter, right? So in that case, our vector theta boils down to a scalar, okay? And in our notation, m, which is the number of parameters, must equal 1, okay? So the assumption that the data is a linear function of theta reduces to this expression here, right? So the theta vector is a scalar, and just by matching dimensions, the matrix H must contain a single column, and therefore it's a column vector, and we denote it by a lowercase letter as usual. And this is the assumption on the covariance, okay? So to find the blue, we will just apply the definition, okay? So remember that the definition specifies that the blue must be a linear function of the data, right? So therefore it can be, it must be expressible in this way for some coefficients an, right? And this is because any linear function of x can be expressed in this way, right? As we know from linear algebra. So the finding the blue estimator is equivalent to finding the coefficients an, okay? So for convenience, we will be expressing this in vector form by stacking the a coefficients in this vector that we are going to denote by a, and the data samples in this vector x as usual, okay? The second condition that we need to enforce is that the blue must be unbiased, right? So to that end, let us compute its expectation, right? Just by this expression here, its expectation is given by this, right? And by linearity of the expectation operator, we can take the A transpose out of the expectation, okay? And now just by using this fact here, or this assumption, then this can be expressed in this way, okay? A transpose H times this scalar theta, right? And the condition that the estimator is unbiased is that its expectation equals theta, right? And therefore we have this equation, okay? So obviously, since this must hold for all values of theta, we need that A transpose H be equal to 1, okay? And the last condition in the definition is that the blue minimizes variance, okay? So what is the variance of this estimator? Well, just by applying this expression, we find that it is the variance of A transpose X, and by using the properties of variance, just applying standard probability theory, this equals A transpose the covariance of X times A, okay? And this is nothing but A transpose C A, okay? That is our second assumption, okay? Now let's put these conditions together, to conclude that the optimal A, the A that we are after, is the one that minimizes the variance, right, and satisfies that A transpose H equals 1. Okay? So this is not a difficult optimization problem to solve. It just involves writing the Lagrangian, and but we will skip the derivation here in the interest of time. You can find the proof in this reference. So the solution will be given by this vector here. All right, and just by substituting this here, right, we obtain our blue estimator. Okay, this is just H transpose C inverse X normalized by H transpose C inverse H. So it's not difficult to remember at all. All right, and just as a sanity check, we will be computing its or analyzing its performance here. Obviously, it must be unbiased if we did things correctly, if this step was correctly done. But since the estimator is linear, we can just compute the bias in a straightforward fashion, right? So we can just take expectation of theta, and note that by this expression it will be just given by this, right? So this expectation enters here, okay? And by using the assumption, we obtain that this expectation of x equals just h times theta, right? So we can express the expectation in this way, okay? And now both of these, the numerator and the denominator, cancel, and we obtain theta, right? Which establishes that that theta hat, the blue estimator, is unbiased. All right. This is what we expected. So regarding the variance, we can also substitute the optimal A here, right? But just to do it in another way as a sanity check, we can just look at the variance of the theta by taking the variance of this expression, which just applying the properties of variance that we discussed earlier. It is given by this term over here, and just by substituting the covariance of x, right, this assumption here, and then the c here cancels with this c minus 1, right, and we obtain in the numerator H transpose C inverse H, right, which cancels with one of the H transpose C inverse H of the denominator, and therefore we obtain this expression here. Okay. Now let's apply what we have learned to our favorite toy example, which is the estimation of a constant in white noise. Okay, so remember that this is our way of saying that the noise is white, and it means that the mean is 0, and the variance of all noise samples is the same, and two different noise samples are uncorrelated. Okay, and we will not be assuming in this case any distribution for W, right? Note that the blue estimator doesn't impose any such an assumption. Okay, and we don't even need to assume that the noise samples are independent. It suffices to assume that they are uncorrelated. So note that this is a more general version of the problem that we have addressed so far. Until now, we assumed that W was Gaussian, and we didn't know how to solve the problem otherwise, right? But now we are empowered by the blue to solve it, even though W has an unknown and possibly non-Gaussian distribution. Okay. So the problem is, as always, given x and sigma square estimate A, although, as we will see, we don't really need sigma square. For convenience, we express it in vector form, as always, okay? And to apply the blue, we need to see if the assumptions are verified, okay? So regarding the mean, we compute the mean. It is obviously 1 times A, right? So 1 will play the role of H, and A will play the role of theta, okay? And the covariance, just by using this expression, is clearly sigma square I, okay? And therefore, this will be our C. We see that the second assumption also holds for that specific C, okay? So, using the expression from the previous slide, we see that the blue estimator is given by this, right? So now we just need to substitute H and C here, right? So H is the vector of all ones, and C is sigma square times the identity. So we obtain this, and now just by canceling these sigma squares here, and also by noting that 1 transpose 1 equals n, right, we come up with this expression here. And this is obviously the sample mean of the entries of x, right? This numerator is just the sum of the entries of x, and this is normalized by the number of entries of x. All right, so remember that we denote the sample mean or average by x bar. And interestingly, this estimator coincides with the estimator that we found, the MVU estimator that we found for the case where the noise was Gaussian, right? So that is very interesting. Whenever the noise is Gaussian, we conclude that this estimator here is both MVU by what we saw in previous lectures, and blue by what we saw in this slide. Okay. And regarding the performance, we can again use the expression from the previous slide, and so we just need to substitute H and C in this expression, and then we obtain this, okay? So this is, of course, expected, because this was the variance that we computed for the MVU estimator. Therefore, it must we just recover the same expression. Remember that this is also equal to 1 over the Fisher information, okay? That's I mean, just remember that that is the case, because x bar in the Gaussian case was not only MVU but also efficient. Okay, just reviewing, connecting with the concepts from previous lectures. Now that we understand the blue when we have to estimate a single parameter, let us look at the more general scenario where we have to estimate an arbitrary number of parameters, right? So let us consider the setup in the first slide, right, with both of the simplifying assumptions, then this theorem states that the blue estimator is given by this expression here, and its covariance matrix is given by this expression here. So the first thing that we need to observe is that they generalize the expressions for the scalar case, right? So in particular, if H is a vector, a column vector, we recover the expressions from a couple of slides ago. Okay, so a couple of remarks. One of them is that the blue has the same form as the MVU estimator for the Gaussian linear model that we saw in the previous lecture, right? So this is very interesting. It has a couple of implications, right? One of them is that under the linear model, if the noise is Gaussian, then this estimator is MVU, because of what we saw in the previous slide, and blue, because of this theorem, okay? And also, if the noise is not Gaussian, then this estimator may not be MVU, but at least it is blue, right? So that means that whenever we find ourselves trying to estimate the parameters in a linear model, we may just use this estimator, and we will have different degrees of theoretical support, right? If the noise is Gaussian, then there are two criteria that support our estimator. If the noise is non-Gaussian, at least we know that this estimator is the best among all linear and unbiased estimators. Let us apply what we have learned to a problem that we are all familiar with, which is the prediction of the number of cases of a contagious disease in the future. Okay, so this will be a simplified version of the tools that are applied to predict the number of cases of COVID-19, for example. So let C of n denote the number of cases of a certain disease on the nth day, right? And as we know, the growth of this number is typically modeled as an exponential function, right? And the reason is that if each person transmits the disease to 2 people, then those 2 people transmit it to 2 people each, therefore 4 people, right? And so on, right? So mathematically, this means that Cn can be expressed as an exponential function, right? In this case, we will have these 2 parameters here, and we will also introduce some error term, right? This 1 plus, we write it as 1 plus epsilon, so that epsilon quantifies the relative error, right? So the need for the error is that the points, the actual numbers don't necessarily fall on top of an exponential, but there is some error, right? And the to be in general, we will just model this as random, but we will not impose any specific distribution. Okay, so we will only assume that the all epsilon n have the same distribution, although that could even be relaxed further. And we, I mean, it's just okay to assume that that this epsilon and that the event that epsilon takes small values is more probable than the event where it takes large values. Okay. So if the values of A and B were known, we could just use this expression to forecast the number of cases in the future, right? One can just set n to be the index of the day of interest, and then one just can set this this epsilon to 0, right? And that would yield a reasonable estimate, okay, right? However, these A and B are unknown, and we need to estimate them from a data set, for instance, provided by a public health authority, okay? So in this case, to deal with this difficulty associated with an exponential showing up in this expression, it makes sense to replace these samples with their logarithm. Okay, so this you can see why this simplifies life. If we take logs here, we obtain an plus b plus the log of this term, right, which here will be denoted as w. Okay. However, there is a difficulty here, and it is the fact that if we compute the expectation of x, we see that it is equal to an plus b plus the expectation of w, right? And the expectation of w is not known, right? We don't know it. So we encounter ourselves in a situation where we have two unknown parameters. They are added together, right? And this should immediately bring to our head and what we said about identifiability in a previous lecture. It turns out that one cannot estimate these two parameters separately, not even b standalone, right? So the way we have to deal with these sort of situations is to condense these two unknown parameters into a single parameter, which in this case is denoted as b tilde. Okay, so we will be estimating b tilde, right, because there's no possible way of estimating b and mu w. But of course, this will not be an issue, right? There would be another possibility, which would be to assume that the mean of w is 0, right? But it doesn't sound like necessarily a realistic assumption. Okay, so let's just go through this path. And by using this notation, substituting it here, we find that the data, or our transformed data, can be expressed as an plus b tilde plus this w tilde, which is just the result of subtracting the mu from w, right? So we have from this left-hand side to the right-hand side, we have moved the mean of w from w into b tilde. Okay. So now stacking these samples to form the data vector x and arranging these numbers in vector matrix form, we come up with this equivalent expression here, right? Where we can recognize that this is the vector of parameters that we want to estimate, and this would play the role of h in what we have discussed today, right? Similarly, w tilde will be a vector containing the samples of and w tilde, right? So with this model, we can just apply the blue, okay? And therefore a natural estimator, right? Or prediction for x at a day n prime, right, could be obtained just by multiplying this vector, right, which would be sort of a row of this matrix, a continuation of that matrix, right, times the blue estimate, okay, of this parameter, right. So this will obviously would give us a value, a prediction for x, okay, at the n prime. If we want to recover or obtain a prediction for c, we just need to undo this transformation that we applied here, and we just take the exponential of that prediction from this previous step, okay. So this provides a way of estimating the number of cases in the future, but I insist that in practice the methods that are used account for other factors and are more complicated than this one, right? But for getting the intuition, I think it is a good example, and it also illustrates how to deal with identifiability problems that we all encounter in our practice as in research or in statistics. Okay, so just to wrap up, we have said that the MVU estimator may not exist, or we may not be able to find it with the tools that we know, or even with other tools on the books. An alternative that we discussed today was to reduce the search of optimal estimators to those that are both unbiased and linear, okay? And that brought us to the notion of the best linear unbiased estimator. This estimator is simple because it is linear, right? Easy to analyze for the same reason, right? And as we saw, it coincides with the MVU whenever the MVU is linear, right? So this provides, in some sense, another way of finding the MVU in that situation. It is warranted to exist under two assumptions, right? That the mean of the data is a linear function of the parameters, and that the covariance doesn't depend on the parameters. But it can, of course, exist if we relax in other cases, okay? What is left for the future is what happens if the blue estimator does not exist. So what happens if these assumptions don't hold, if the statistics, specifically the mean, doesn't depend linearly on theta? What should we do in those cases? And this is precisely what we will answer in the next lecture, okay? So thanks for your attention, and see you in the next video.